Well, I will begin with a word of prayer. Ahem, hem, hem, hem. Heavenly Father, we thank you for this day. I thank you for the students, for the break that's about to start. Lord, help us use this time wisely. Lord, in your name I pray. Amen. Well, you are part of a select few, those who are actually still at school right now. Like the parking lot is really do top hat today. I am at least 10 times. I guess that would make up for all the times I haven't done it in other classes this week. Ha 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 ha. 10 hat Tuesdays. 6, 4, 4, 7. Where was that fire alarm? Where was that fire alarm? I heard it walking in the other day.
No, it was at Commons at like 2 a.m.
Oh, because there was one, I was walking here the other day and it was...
Oh, yeah, I heard it.
Yeah, I don't know where that was from. Why is this not working?
There was some freshmen and a microwave and That's almost always the We're the third quarter. Tasting of the third quarter.
All right, let me talk about the math battle solutions briefly. This shouldn't take too long. So I hope you guys realize, after everything's said and done, that in fact the worst problem here was number 12. Numbers 4 and 5, actually, once you see past the new ideas, they're not that bad really. But maybe you haven't seen that yet. Anyway, so the first one is just straight up, an inverse tangent integral. I can find it by trig substitution. If you were in Dr. Sperano's Calc 1, you may have been taught this as kind of like a basic form, right? But anyway, however you know it, this is the antiderivative of that is 1/3 inverse tangent of, that's supposed to be, son of a gun, that's supposed to be divided by 3. Yeah. So the good news is I have not graded your math battle, but I think if I did that, I would have figured out the mistake in my solution here. So the moral of the story is I shouldn't try to help you guys and write a solution at the same time. Now the interesting thing is this doesn't change, right? You divide that by 3 as t goes to infinity. It's still, that term is still going to be pi over 2. So like the pi over 6 is right? But it's the inverse tangent. It should be inverse tangent of 5/3, I think, rather than just 5. Yeah? Is that what you guys got? Inverse tangent of 5/3 over 3. Didn't get there? Don't remember? All right. Fair enough. Arithmetic aside, this would not be a bad test question, right? Everybody can do this? Number 1? I hope. Well, if you don't have confidence about doing that, I would recommend finding some. Let's see here. Okay, so problem 2. Let's see here. So I have natural log of ax over x cubed. We can integrate by parts, right? So u equals log of ax, and dv is dx over x cubed. So integral of dx over x cubed is minus 1 over x squared. And du is dx over x. All right, the a's cancel. If you had the misfortune of not canceling the a's, that makes the resulting algebra later impossible. So, sorry about that. I did tell you over here what you're supposed to do, because somebody asked me about it. Okay, anyway, after the integration by parts, use FTC2. That gives me this limit. You know, this integral from 2 to t gives me that, right? And so I've got log a t over t squared minus 1 over t squared, and then this term over here. I put the t squareds together, gave me that. This is just a constant, so I pulled it out. Then going from here to here, L'Hopital's rule gives me 1 over t, differentiate the top, get 1 over t, differentiate the bottom, get minus 2t. That results in a minus 1 over 2t squared, which goes to 0, leaving us this. Yep. Oh, have I done this again? Oh, phooey. All right, yeah. All right, so we have learned an important lesson. Do not try to help you guys during math battle. Focus on my own solution. That is the lesson I've learned here. Okay, so dv over x cubed. Oops, dv is, what is it? Dx over x cubed. So v is what? Thank you, 2x cubed, 2x squared, right? Yeah. And with that modification, that doesn't change anything about the part that goes to 0, right? But it will change the, that puts a 2 out front as well. That just makes that an 8, right? The fourths become eighths, is that right? Yeah. So we should have natural log of 2a. I mean, cutting through the noise here, this should be what we get for the second piece, which doesn't go away. And then in the thing I haven't showed yet, that's going to be set equal to 1, because if we integrate from minus infinity to infinity, I tell you, what was that? So the integral from minus infinity to infinity just is that integral, because everything else is defined to be 0. So I set this equal to 1, which gives me log of 2a plus 1 equals to 8, which gives me log of 2a equals to 7, which gives me that 2a is equal to e to the 7th. Therefore, a is equal to 1/2 e to the 7th. Is that what you guys got? Nobody got that? You got that? E to the 7.5. Huh. Interesting. I mean, but up to arithmetic mistakes, that's how you solve this one, right? Let's see here. Problem 3. So I'll try to fix my mistakes and repost the solution, obviously, right? Here, if you look at the list, it's easy enough to see that minus 1/2 is below everything, and 1 is above everything, right? And so those actually, since those actually are the min and the max respectively, they will serve as the infimum and the supremum. And in this case, I could even find the min and the max or those things, for what it's worth. The next one, part B, I think you guys found more challenging, right? But if you look at it, you ought to be able to see that, first of all, since A is positive, right, and R is between 0 and 1, we're taking something positive, adding something positive, adding something positive. So if you look at it, this is definitely an increasing sequence, right? Which means it's bounded below by its first term. A is less than or equal to x, right? I say by inspection. What's that mean? By looking at it, that's right. right? In other words, by common sense. Also, the limit as n goes to infinity of k equals 0 to n of ar to the k, which is after all what this is, right? This is the partial sum of the geometric series. That limits to a over 1 minus r because we're given that 0 is less than 1, 0 is less than r less than 1. It's a geometric series, right? So I know the limit of these terms is a over 1 minus r. I also know it never quite gets there at finite values, right? So this, using the bounded monotonic sequence theorem in that larger discussion, serves as a upper bound, in fact, the least upper bound. So that's the supremum. The supremum is a over 1 minus r. It's not equal to the max. I didn't ask you about whether it was equal to the max or min, right? I'm just saying it's not equal to the max because this actually isn't in the set S, right? It gets closer and closer and closer to that, but never gets there. On the other hand, the infimum is just a. So problem 4, I was trying to introduce you guys to, I talked a little bit about it Wednesday before the math battle at the very end of class, but I understand that was probably not enough to understand it, and that's okay. I was hoping that by the exercise of this problem, some of you might understand. And the idea is simply this: if we have a recursively defined sequence, which can also be stated in terms of a single function of the previous term. So not everything is like this, right? Like Fibonacci sequence does not fit this pattern. We can't always find a generating function for every recursively defined sequence. If it's based on like more than one step back, further thinking is required in terms of quote-unquote generating function technology. But in this case, if there's a single function that allows us to capture the recursion like so, then we can look for its limits. Because if you do have a limit, if you think about the defining relation for the recursion, you take the limit as n goes to infinity of this, it must be that the limit a is equal to f of the limit, which is f of a. So that means that the value to which the sequence converges must satisfy this fixed point condition. In other words, that a is equal to f of a. Notice that a equals to f of a is just a plain equation, completely divorced of any like sequential anything. It's just an algebra problem, right? And so like part B, I can find the fixed points of this function by just solving f of a equals to a, which is a is equal to a over 4 plus 3/4, which gives you a is equal to 1. Was I able to do the algebra correctly here? Okay, I'm genuinely asking because apparently I'm not thinking clearly when I wrote this. But I think this is right because I have independent verification. So then I went and tried to find the formula, right? How do you find the formula? You just start working through the iteration and then you start looking for patterns. In other words, by inspection, right? Finding formulas is by inspection. So after I calculated a few, I'm like, wait a minute, there's a pattern here. It's always like 4 to a power plus 1, you know? 4 squared plus 1, 4 to the 1 plus 1, 4 to the 0 plus 1, 4 to the 4 plus 1, right? 4 cubed plus 1, rather. And so I realized that's 1 plus 4 to the n minus 1 over 4 to the n minus 1, which of course you can algebraically simplify to that. So there's a formula, right? And then as n goes to infinity, it's clear enough that the limit of this sequence is just 1, right? Well, from the boxed formula, it's obvious, right? But that's also what we found from solving the fixed point equation up here. And since there was only one fixed point, it must be that that was the limit of the sequence if it exists, right? How do you know if the limit exists or not? Well, if you get a bounded sequence that's monotonic, you know that the limit exists, right? And this is such a thing. So the larger point here in part C is it's not everything we've looked at in here except for the next problem. Recursively speaking, I was able to see a formula for this semester. Like the problems I've inadvertently chosen for you guys, it's always worked out that there's a formula to be found for the recursively defined sequence. Ignoring, of course, Fibonacci, right? I mean, Fibonacci, I don't know a nice closed form formula for that for you guys, right? But everything else had one. Not this one, though. So problem 5, if you look at, following the logic of problem 4, look for the fixed points, right? F of a equals to a gives us this. which you can solve to either give you a equals 0 or a equals 3. All right? Which is the limit will depend on where you start the sequence. If your a sub 0 is 0, the limit would be 0. But if your a sub 0 is pretty much anything else, it will drag the thing to 3. I'm pretty sure. I've tried some different values. Certainly, if we start with a sub 0 equals to 2, and you start following the recursion, you'll get numbers closer and closer to 3. Check it out. So like the square root of, square root of 2 times 3, 2.45. The square root of 3 times the square root of 3 times 2, or the square root of 3 times the square root of 6, 2.71, and then the square root, 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 square root. And it gets closer and closer to 3, right? But the cool thing is, you could figure out that this is going to 3 with a fair amount of certainty by just solving the fixed point equation and doing a little bit of numerics. So we can see that the limit as n goes to infinity is 3. All right. So I definitely want part of the next test to be like this, right? One problem where I just say use intuition, write a brief sentence. This is more. What I've written here is more than you need to write to get full credit on the intuition problem. Like on the intuition problem, you don't have to explain to me why tanh goes to what it does. I'm saying that so that those of you who didn't know that have a reason why. But this right here is just me trying to, again, teach you that tanh goes to 1 as x goes to infinity. We've talked about this before, but many of you have forgotten this, right? So because tanh goes to 1, that means that a sub k goes to 1, because this is getting really large, and we're feeding it into a function which asymptotically goes to 1 for large values, right? So by the kth term test diverges. But I would be completely content if this was the problem on the test, if you just wrote, this looks like it diverges by the kth term test because tanh doesn't go to 0 as its input is large. Like that would be a totally acceptable solution to this problem if it was on the test, all right? I want to try to communicate to you what I mean by intuition. I don't mean quite as much as I have written on this solution. Yeah.
Doesn't tanh go to pi over 2?
That's inverse tangent goes to pi over 2. This is hyperbolic tangent. Yeah. Now, the next one, basically I'm just looking for you to go, if you just look at what matters here for really large k, this is essentially just 1 over, that's a 3/2, believe it or not. 1 over k to the 3/2, which of course is convergent by p equals 3/2, right? How would you make b rigorous? What would be the easiest thing to do? If you wanted to give a careful argument for why it was convergent, what test should you use? Which I hear one vote for direct comparison. Any other votes? Yeah. Yeah, I think limit comparison is one you want to go with here, because direct comparison is kind of well, to quote the young and eager go-getters that are currently in various positions of power here, it's a big ask. So like a direct comparison, I got to find something that's larger and converges. So to find something larger that converges, see, I've got pluses down here. If I get rid of those, that makes this, I can do that, right? I can get rid of the pluses. But then the trouble is upstairs, I've got plus as well, right? So to get something larger, I guess you could replace the 2 with k squared. I mean, it's not impossible to do direct comparison. I just think it's intellectually lazier to do limit comparison, just some algebra, yeah.
Is it possible when you have something like that has pluses on the top, that you could split it into 2 fractions and do like direct comparison for both parts of it?
Oh yeah, that's also, sure, I totally endorse that. She's saying you could split it into 2 and do direct comparison on 2 different pieces. You could do that, sure. Whenever we split, it always, like I said, kind of takes out a logical loan, in the sense that once you split, it's only like legitimate after you've shown that the sort of daughter sums are themselves convergent, right? But yeah, sure. This one here, oh, there it is. So what do you guys think about this one? So what I said was definitely convergent because I just look at it essentially and go, k factorial wins. And honestly, we've already worked out that 3 over k factorial is convergent. So I know this is convergent because it's like, it's smaller than 3 to the k over k factorial, which is something we already worked out in class. I mean, that would be another legitimate reason. But here's a self-contained reason that this is less than that, is less than that. But listen, if you write anything that is kind of quasi-reasonable and make the right answer, then you'll get full credit for the intuition one, right? I'm probably not going to take off points as long as you say something and it's not just completely out to lunch, right? Like, you say something like don't write like, I like soccer, it's a legitimate sport. You know, if you were to write that as your reasoning, then, you know, you'd be wrong on two different levels. So, you like soccer? Oh, okay, sorry. Oh, okay, so then problem 7. This one is, as I forecast you guys, you can do the algebra and rewrite this as 1/2 k plus 1 minus k plus 3. And then if you write out the nth partial sum, it should simplify to this. Take the limit as n goes to infinity. That goes to 0. That goes to 0. It just leaves you with 1/2 of 1/2 plus 1/3, which is 5/12. And so that's the sum of the series by direct calculation. This is what we commonly refer to as a telescoping series. Right? You had another one in your homework that was like a difference of inverse tangents, right? That was also telescoping. But there was no partial fractions to do, right? It's just telescoping because the formula I gave you was based on a difference summed. This one's geometric. So you just got to look at it and realize that that's 9 times e squared over 9 to the n. E squared is about 7 point something, so that's a fraction less than 1, which means that the radius, or the ratio, if you like, of the geometric series is legitimate and for convergence, which gives us that. And again, if I often ask a question, calculate the sum of the series if possible, what do you got to be looking out for? Make sure you don't miss, credit for doing that. What are the 2 kinds of examples you got to be looking for to make good on that instruction? Geometric series or telescoping series, right? Got to be on the watch out for those. If I say calculate the sum if possible, those are the 2 possibilities for you right now. That is not quite true. There's one other possibility, which is like it's a sum of those things. We had an example where we had like 2 different geometric series added together, so that's also possible. But that's about the highest our pay grade allows for at the moment. Question? This one here, I said calculate the sum of the series to within 0.01. So this is an alternating series estimation theorem problem. You just got to look at the terms and find the one that's less than 0.01. So if you look at 1 over 5 factorial, that's 1 over 120, which is 0.0083. That is less than 0.01. That means that if I just keep the first 2 terms in this alternating series, that approximates the true sum within that value. So in fact, this is about 5/6, plus or minus that. Yeah.
Why isn't it the first 3 times of 5 factorial is 1 over 5 factorial plus 1? Shouldn't it be like...
If I kept the first 3 terms, I could do that. It would also answer the question, but it wouldn't be the laziest answer. So like if I kept the first 3 terms, then that is good to within 1 over 7 factorial. It's always the next thing you don't keep that bounds the error. So like by keeping the first 2, I know that I'm within the next term of the real answer. If I kept the first 3, I'm within 1 over 7 factorial of the real answer. This is the alternating series estimation theorem. Yeah. I hear what you're saying, though. show that's absolutely convergent. So root test shows it converges, done, right? If the absolute value of the series kills the what? What's absolute value do? It's the natural enemy to -1 to the k, right? So that just leaves you 1 over k to the k, which is like the quintessential root test problem, right? All right, moving along, problem 10. This is just a straight direct comparison problem because it's kind of like 1 over n, right? The thing is that this is positive, so if you drop it from the denominator, that makes the denominator what? It makes it the denominator bigger, which makes the fraction smaller. And that, of course, gives us 1 over n, which sums to the harmonic series. So this diverges, the series of this diverges, of course. Consequently, this must also diverge by direct comparison test. Okay? And I just restated the direct comparison test down here. Obviously, you don't have to do that in your solution, you know. Problem 11. Hey, look, one of your homework problems, right? Which one was this in your homework? Am I wrong? In the mission, right? Oh, it's further down? Problem 82. So we're currently looking at the solution to problem 82. What do you know? Oh, some of you are just learning this now? I guess there's still time. Sort of. All right. So this is just really ratio test, and you have to be careful with the algebra. So to do the ratio test, we have to calculate a sub k plus 1 over a sub k. The key to being successful at a problem like this is understanding how to manipulate factorial carefully. So k plus, and this is also an important trick, to divide by a sub k, multiply by the reciprocal of the formula, right? So k plus 1 factorial quantity squared. The key here is that k plus 1 factorial is k plus 1 times k factorial, right? So I did that. And then down here, we've got 2 times k plus 1. Well, that's 2k plus 2. So that 2k plus 2 factorial is 2k plus 2 times 2k plus 1 times 2k factorial. The reason I'm doing this is because I know from past experience that you're looking to cancel, you're looking for some sort of algebraic manipulation of the formula for the kth term in the sequence that makes, that finds the commonality between the k plus 1th and the kth term so that you get cancellation. That's how every ratio test problem that's successful works out. And it just happens that that's the mechanics of the algebra here, all right? And when you do that and you square it, you get a k factorial squared up here. It balances out the k factorial squared down there. And you get a 2k parentheses factorial up here that balances that 2k factorial down there, which just leaves you this quadratic over that quadratic, right? Which is good news because regular rational function algebra reveals that that has a limit of 1/4, which of course is pretty awesome because then that means the ratio test applies and shows that this series converges, right? Because we found a lambda which is less than 1. Questions? Well, this has been posted since yesterday, right? So, yeah. Complete with the errors in the first two problems. Hey, but none of you emailed me about those errors yet, so I can safely assume that you haven't been working through it and confused, right? I hope when you're working through something and you get confused, you'd send me an email. I'm not bothered by that, you know. Problem 12. Problem 12 required some thinking. So what I did was I defined this function f of x equals the log of x minus x to the pth power, pth root. I differentiate it, and I figure out, well, to figure out whether this is positive, whether this is the derivative is negative, it suffices to get that the numerator is negative for sufficiently large x, because if x is positive, the only way this can be negative is if the numerator is negative, so it gives me to this. But if I look at star, I can trade it for this, which I can trade for that, which I can trade for that. So if I have that x is greater than p to the p, it implies that f of x is decreasing. Now, you could have the annoying thing that it decreases towards some limiting, like some asymptote, and never crosses it, and yet is decreasing forever and ever. That's possible, right? But the thing is, if the function gets negative at some point, if it's always decreasing for very large values of x, it has to stay negative past that point, right? So it suffices to find one point, which the function is negative for, if I want to prove that f of x is less than 0 for all x sufficiently large, which is my goal. So I plug in p to the 2p. You might wonder where p to the 2p comes from. It comes from me tinkering with the p equals 10 case, or 2 case, or something. But if you do plug in p to the 2p, you get this, which is 2p log p minus p squared, which in fact is less than 0. Now you might go, 2p log p minus p squared, why is that less than 0? Well, I'm glad you asked. If we look at the function g of x equal to log of x minus x over 2, and we differentiate that, it gives me 1x minus 1/2. And if x is greater than 2, then clearly this is less than 0, hence g is decreasing. But if you plug in 2, you get something that's less than 0, which means that g of x is going to be negative for all x larger than 2, which is to say that this inequality is true. This is the same as that, actually. Anyway, so this what's between these two lines justifies star star. Having justified star star, I have now shown that the inequality I want is true. I've shown that f of p to the 2p is less than 0, and consequently f of x beyond that is negative. All of this as a means to prove that the natural log of n minus the pth root of n for n greater than or equal to 2p is less than 0, which gives me this, which if I take the pth power gives me that, which if I rearrange gives me this. And by the way, this is what motivated the whole thing. All right, like this is where f of x came from, was the desire to show this inequality is true. To show this inequality is true, it became a quest for showing that the log of x to the p minus x is negative, but it's easier to look at this being negative and looking at the function that defines that to show it's negative. There's probably some easier way of doing this, but anyway, once you have that, then we can do direct comparison to the harmonic series to see that that diverges. So rather than solving the 1 over natural log of n to the 10th power problem, I figured I might as well solve the 1 over natural log of n to the pth power problem, since it's the same annoyance. This is a particularly ridiculous example of direct comparison test. Check this out. This comparison requires you to be larger than p to the 2p. So for like n equals 10, the direct comparison starts at 10. For p equals 10, for the problem we looked at in class and got stumped on, right? And now we see why. Because this is a dastardly problem. You know where this problem came from was the ratio and root test section. I copied this from the ratio and root test section because I thought maybe this was a legitimate example for ratio root test. What happened to us with ratio and root test for this thing? They failed. I tried limit comparison for arbitrary p-series against an arbitrary p-series. It doesn't matter what p-series you choose. They all fail for the n equals the p equals 10 one. You have to solve this by direct comparison, as far as I know. Sorry. But you know, think about p equals to 10. The direct comparison starts at 10 to the 20th power. Good night. Anyway, there it is. It diverges. Of course, the easiest version of this problem is just the sum over log n. If I just had sum over log n, then I think most of you would be comfortable stating this inequality if you thought about it for a little bit, right? I drew a graph that shows you that this is true, right? N is always over log n. If you want to prove it, here's the details to prove it. Similar arguments that I've given today, but this is true. So if n is greater than log n, 1 over n is less than 1 over log n. So by direct comparison, this diverges. So like, this is the test-worthy version of this problem, all right? Or what's the way to make this problem like a reasonable test problem is simply to give you the thing that I had to work so hard to prove, which was what? This, right? If you're given this inequality, then the problem becomes not so bad, right? That was the whole trouble. Is there a problem you guys like to talk about in mission 2 in particular? Maybe I could just tell you what the answer is at the moment, you know? If you ask me, if I might be able to find it. Tell you what. I had another idea. I want to show you guys something. So I'll make a link to this. So this is the resource page for the online class, which is generally irrelevant to you guys because we have 5 days a week we meet and we cover pretty much everything in class, right? So that's why I haven't emphasized this too much, but it is here. And there are, 40 some odd PDFs I posted with sample problems from the different parts of the course, right? So one of the things that accompanies this, if you're searching for additional instruction, is the playlist. Come on. The playlist and what this playlist has is about 10 hours of videos. And many of these videos accompany the PDFs, which I just showed you. And and they do have the benefit of you don't have to actually see me. Let's see here. But eventually, maybe this video in particular would be very useful to you. Summary of convergence tests. So like here, in this video, isn't this very meta, right? If I had brought I should have brought you know what that is? Is it not playing? Oh, there it is. Yes, this is a Star Wars chopstick. I got it for Christmas. It's awesome. But this is the thing I haven't done in class yet, right? Which we probably would do Monday after break because, But here's the grand scheme, how I think about, and you don't. It's not written in stone. You have to think about it this way. But when I think about the convergence or divergence of a series, this is kind of the picture I look at, roughly speaking. So what I mean by this picture is if I'm given a series and I'm trying to ascertain its convergence or divergence, there's some things that I just do by inspection. Is it a p-series? Is it geometric? Does the nth term test rule it out, right? All of those are sort of first level, basic attacks to solve the problem. So I'm really thinking about all of those simultaneously, p-series, nth term test, geometric, also alternating. Like if it's alternating, you can usually just see it, right? So if any of those methods of attack settle the question, you're done, right? If that doesn't work, then the next thing I go to typically is direct comparison, right? And then I ask myself the question, is it worth it? If I'm working too hard on the direct comparison, I ask myself the question, should I really be doing ratio test, limit comparison, root test, right? This, I almost think, should be down here somewhere. This is my last preference. I really don't like the integral test because it requires so much, intellectual capital to start. I need to show that the function's positive, decreasing, has limit 0. And after all that, I still got to do an integral. You guys like integration? Why are you taking this course? Sorry, I'm a jerk. There's also absolute convergence. Hey, stop that. So this is roughly my plan, as I say, right? And then, so then I go through like, I don't know, a dozen different examples. And so anyway, this has a pretty complete, wait a minute. Is that one of your, come on, YouTube. Oh, anyway, I will send you guys a link to this particular video. Yeah? Yeah. I guess I probably need your homework. Yeah. You could pass your missions to the center. I'll collect them. So hopefully the camera worked today. I'm not sure my camera's not, I'll get it. It's fine. I'm a little bit